Everyone, in today's lesson, we're going to talk about what we call higher order derivatives. So far, you've only learned the notation. If I have given you y, we can say y prime is a first derivative. If I give you f of x, we say f prime. If I give you y, I could also say dy dx. So all three of these things are okay for the first derivative. Now, what we're going to talk about today is higher order, which means I could go to a second derivative or a third derivative. So notice the second derivative notation has two primes. And in dy dx, we have squareds. Third derivative, same thing, there's three primes, or in the dy dx, there's threes. So after the first, second, and third, we move away from tallies, these primes, and we go to actually just writing the numbers. So if I had, like, say, the fourth derivative, it would be y4, or f4 of x, or d4y over dx4. So if I have an nth derivative meaning 4 or higher, it's just y to the nth, fn of x, and dny over dxn. So that's just, textbook definition. So let's do a couple of examples with this. So question number 1 says, if f of x equals this, then evaluate f prime. We know that. That's a power rule. So we can simply take the derivative by taking the 6, bringing it in front, decreasing the power by 1. And we can keep going. So minus 8x to the third, plus 10x, and then plus 3. So what a second derivative means, take the derivative of the derivative. So let's do another power rule now. So 6 times 5 is 30. Keep the base, decrease the power by 1. Keep going. 8 and 3 is 24. Keep the base, decrease the power. And the derivative of 10x is just 10. Third derivative means take the derivative of the derivative. So, or the second derivative. So 3 times 4, or 30 times 4 is 120, x to the third, minus 48x, and then your derivative of your constant is 0. And last but not least, we could take the derivative of this. 120 times 3 is 360, x squared, minus 48. So taking higher order derivatives, not too bad. Now I can make it a little bit harder by asking you something like this, right? So here's y equals, and I want you to take the derivative, and then I want you to take just the second derivative. So I notice that I have a radical here. It would be in your best interest to know that the square root of x is the same thing as saying x to the 1/2. I would probably rewrite that. So when we take the derivative of x to the 1/2, the first derivative, we take the 1/2, bring it in front, so 1/2, keep the base, decrease the power by 1. So 1/2 minus 2/2 is negative 1/2. And then the derivative of this piece is just a simple power rule. Take the negative 2, bring it in front, keep the base, and decrease the power by 1. So now if I want d squared y over dx squared, that's the same thing as saying take the second derivative. So we're going to multiply the negative 1/2 times the 1/2. That gives me negative 1/4. Keep the base, and decrease the power by 1. So negative 1/2 minus 2/2 is negative 3/2. And then the second term is just another basic power rule. Take the negative 3 times the 2, give that to be 6, keep the base, and decrease the power by 1. Now just know that these derivatives can also be rewritten. I could change my negative exponents, bring them downstairs. I could even make them into radicals as well. So I'm going to just do this last one just to show you. So I could take this term, bring it downstairs with the 4. So the negative 1 stays on top, 4 can go on the bottom. 2 is my root, 3 is my power. So I could say the square root of now x to the positive 3. Same thing with the second term here. I can take this guy, shoot it downstairs. So 6 over x to the 4th. So either way, you could leave it like this. If it's a free response, you can leave it like this. But just know if it's multiple choice, you'll likely see it in that form. Okay, well, example number 3. So I need to now take the derivative, the second derivative of this. What you should notice is that it's difficult to get y by itself. So we're going to need to use implicit differentiation. So that means we're going to take the derivative of each piece. So I see a trig, so I'm going to put sine, cos, negative cos. And I want to take the derivative of sine. So the derivative of sine, we look to the right, is cos. So cos y. but we took the derivative with respect to y, so I need a dy dx next to it. Next term, the derivative of x is just 1, and the derivative of y is also 1, but we need to multiply by dy dx. So we're going to get all the terms that have dy dx on one side, so cosine of y times dy dx. And this term, actually, let me clean this up first. 1 plus, I don't need that 1 in front. I'll just call this dy dx. So I'm going to minus this dy dx on this side. So I have cosine of y dy dx minus another dy dx equals 1. And what I'm going to do now is take out my GCF of dy dx. And when I do this term divided by this term, the dy dx is cancel. I'm left with cosine of y. And then dy dx divided by dy dx, that's 1. Anything divided by itself is 1, equals the one that's over here. So my dy dx is 1 over cos of y minus 1. So that is your first derivative. But now the question was asking you to find the second derivative. So we're going to do another implicit differentiation, which means take the derivative of everything you see here. So because I have a fraction, we're going to use a quotient rule. We'll call this high, we'll call this low. So the derivative of the left side of the derivative of the first derivative, dy dx, we could just write as d squared y over dx squared. And we know it's a quotient rule. So low comes first. So low, cosine of y minus 1. In parentheses, that's your low. D high is 1. What's the derivative of a constant? 0. So low d high minus high, which is 1. And then d low. D low is the derivative of this. Well, the derivative of cos, we can look over here, is negative sign. So negative sign of y. But since I took the derivative with respect to y, I need a dy dx. And the derivative of this constant is 0, so I don't need that, thankfully. I don't have any room. And then the bottom is low squared, so cosine of y minus 1 squared. So we can clean this up a little bit. D squared y over dx squared is simply anything times 0 is 0. Negative times a negative is a positive. So we can write this as sine of y times dy dx over cos of y minus 1, that whole thing squared. It's ugly, but this is totally fine and acceptable for my second derivative. Okay, you're probably wondering, what do I need all this for? So let's take a look at some multiple choice questions in the back. Okay, so example number 4 says, a curve is given by this equation, and it has a slope given by this equation. Find the value of d squared y dx squared at the point where x equals 2. So in example 4, you should notice that this is implicit. They already proved and told you what the first derivative was. They want to find the value of the second derivative. So they want to find the slope, d squared y over dx squared, at the point where x equals 2. So you don't need to find the first derivative because they found that for you. So that's great, that's helpful. So let's say first derivative. So we want to find this. So I'm just going to start by writing dy dx. I'm going to rewrite my first derivative of negative 3x squared y, negative 3x squared minus y over x. So I want to take the derivative, same as I did before. Here's my high, here's my low. So my second derivative is written as d squared y over dx squared. So the formula, low times d high. Well, the derivative of the high, power rule here, negative 6x minus derivative of negative y is negative 1 times dy dx. So that's my low d high minus my high, negative 3x squared minus y, d low. Derivative of low, derivative of x is just 1, all over low x squared. So I'm just going to clean this up a little bit. D squared y over dx squared. So I'm going to leave this just as x and then negative 6x, but instead of minus 1, I don't need that 1, right? 1 times anything is that thing. So minus dy dx minus negative 3x squared y. Again, I don't need that 1 because 1 times anything is itself. All over x squared. I can drop the parentheses. They're not needed anymore. So they want to know the value of d squared dx squared, which we have, when x is equal to 2. So you should remember with implicit that we always need a point. We don't have a point. We just have an x value. So in this problem, you need to find the y value. So find y when x equals 2. And you know, in order to do that, you need to use your original equation. So my original equation is x to the third plus xy equals 8. When x is 2, 2 to the third plus 2y equals 8. So 8 plus 2y equals 8. Looks like I can subtract the 8's off. So 2y equals 0 divided by 2. Y equals 0. So my point is x 2, y 0. So how is this helpful? Well, if I want to evaluate d squared y over dx squared at this point, I'm simply going to plug in when x is 2 and y is 0. So let's go ahead and plug that in. So x is 2, x again, sorry, x is 2. And dy dx, I'm going to leave that blank for a minute, minus negative 3, x is 2, y is 0, all over 2 squared. So I skipped over this dy dx, right, because that's supposed to go here. So what's interesting about this whole implicit concept is that you actually have to go back to your first derivative, which is here, my dy dx, and I need to plug in the point here as well. So let's do that. So when x is 2 and y is 0, let's see what dy dx is. So I'm evaluating dy dx at the point 2, 0. So 2 times 2 is 4, times negative 3 is negative 12, minus 0 is negative 12, over 2 is negative 6. So this dy dx, we're evaluating at that same spot, is negative 6. It's double negative here, so we'll just change that to a plus. So that's the hard part about a second derivative, is that you also need to find the slope at the first derivative in order to plug it in for the second. So let's see if we can finish this without a calculator. So we've got here 2. Negative 6 times 2 is negative 12, plus 6 is negative 6, minus 2 squared is 4. 4 times negative 3 is negative 12, minus 0 is nothing, all over 2 squared, which is 4. So negative 12 plus 12 over 4. Oh my goodness, all this work for 0 over 4, which is 0. So this is your final answer for my second derivative. Whew. Okay, so I think that's the last example that I'm going to do with you guys. And I'm going to say, please try example number 5 for homework. And we will start class by going over this one tomorrow. Just look at your answer choices, by the way. Everything is in decimal form. So I'm thinking we might need to use the calculator for it. This would be a calculator active question. So feel free to use the calculator. All right, I'll see you guys in class tomorrow. Have a good night.